Welcome to The Explainer. Today, we're going to absolutely demystify the so-called magic of AI. We hear about artificial intelligence all the time as this mystical, autonomous force, like it's some digital brain just conjuring brilliance right out of thin air. But today, we're pulling back the curtain. We're going to reveal the actual, gritty human ingenuity that's really powering the whole shebang. We're talking about celebrating the brilliant human authors and researchers who painstakingly built the incredible architectures of modern computation.
Let's dive right into this by asking a question that might honestly shatter how you view your phone, your laptop, or your favorite chatbot. Do computers actually process meaning? Think about it for a second. When an AI writes a beautiful poem or codes up a complex website, is there a conscious entity inside that machine, truly thinking for itself? Well, as we'll uncover today, that illusion is totally backward.
To really ground this reality, I want you to think about this staggering number. 80 to 90%. That is the chunk of AI compute cycles that are actually just tensor operations. Yeah, they aren't deep, meaningful thoughts. They are literally just mathematical approximations. Instead of knowing what a word means, the machine is performing massive statistical calculations to just mathematically guess what word usually comes next. When large language models do their heavy lifting, they aren't calculating an absolute ground truth reality. They're just making highly educated, incredibly fast mathematical guesses.
1. The grand AI illusion. 2. The hardware bottleneck. 3. Turbo-quant, compressing the cache. 4. LARCO, querying the black box. And 5. The return of the author.
Section 1. The grand AI illusion. So, exposing the physical and mathematical constraints that bind modern computation really requires a shift in perspective. If you're a fan of classic sci-fi, you'll immediately recognize the idea of the universal Babelfish. Generative AI isn't an independent thinker at all. It's essentially just a mechanical mediator. It blindly translates human associative thought into discrete digital tokens. It maps structural sequences and patterns without actually comprehending a single word it outputs. Ultimately, you are the source of the creativity. The AI is just a highly efficient translator, bridging the gap.
Section 2. The hardware bottleneck.
This brings us to the actual physical copper wires that hold these massive models back. It's known as the von Neumann bottleneck. Since way back in 1945, computers have physically separated the processor from the memory. Imagine a brilliant, lightning-fast chef who is forced to walk miles to the grocery store for every single ingredient. That is your AI processor. Because an AI requires evaluating billions of mathematical parameters for every single word it generates, it creates a massive data traffic jam. The processor literally just sits there, idle, waiting for model weights to be shuttled back and forth from memory, wasting immense energy and strictly limiting the AI's context window.
Section 3. Turbo-quant, compressing the cache.
Now, to attack this physical hardware memory limit, we have got to proudly celebrate a group of specific researchers: Emir Zandia, Majid Daliri, Majid Hadian, and Vahab Mirokni. It's their foundational sweat of the brow, their painstaking, intentional mathematical labor that built the architecture to conquer these physical limits. They engineered a precise, data-oblivious pipeline called turbo-quant. And a data-oblivious pipeline simply means it can process data with incredible efficiency without ever needing to interpret or understand the underlying content it's handling.
The core of their invention is startlingly elegant. Before quantizing a vector, turbo-quant simply applies a random geometric rotation to it right within its high-dimensional space. That's literally it. This ingenious rotation achieves near-optimal distortion rates, highly compressing the KV cache, which you can kind of think of as the AI's short-term memory of a conversation. It squeezes this massive memory footprint down to just 3 or 4 bits, completely bypassing the need for any complex, time-consuming codebook training stuff.
And the results of this human mathematical ingenuity? They're massive. We're talking about up to an 8x performance boost on heavy-duty H100 GPUs when comparing the new 4-bit turbo-quant to the old unquantized 32-bit standard. And the absolute most remarkable part is that they achieved this huge reduction in memory overhead with zero loss in accuracy. No way, right? But it's true. It's an absolute game changer that lets developers run massively complex models way more efficiently.
Section 4. LARQL, querying the black box.
Well, beyond hardware limits, we also face the opaque, uninterpretable nature of neural networks themselves. Traditionally, a neural network is a true black box, right? It's a massive soup of billions of numbers interacting in ways that even its creators can't easily trace. But enter another brilliant human architect, Chris Hayuk. He looked at those dense, opaque neural weights and decided to treat the frozen large language model not as a mysterious black box, but as a structured, queryable relational database. He developed a framework called LARQL, which strategically decouples the model's attention mechanism from its feed-forward network, finally letting us safely query what the model actually knows inside. Hayek achieved this breakthrough by decompiling standard transformer weights into what he calls a vindex, or vector index. Think of this like taking a fully baked cake and magically unbaking it, separating it back into flour, sugar, and eggs so you can inspect the exact ingredients. A vindex is a structured representation of the model's feed-forward layers mapped directly into memory. This unlocks the unprecedented ability to trace the exact inference paths and literally audit the model's internal beliefs layer by layer.
Within this same ecosystem, we absolutely have to celebrate Mike Moring and the pioneering team at DaVinci AI. Traditionally, if an AI learned a bad fact, you'd have to spend thousands, sometimes millions of dollars in compute costs just to retrain the entire model. But Moring took these abstract database queries and turned them into tangible, targeted knowledge patches. This brilliant engineering allows for instant, lightweight knowledge editing of the model, totally skipping the massive financial and computing burden of retraining from scratch.
This builds into a complete, highly efficient workflow. First, you extract the vindex. Second, you write your specific LARQL query. Third, you build a patch overlay. And fourth, you apply it instantly. We are talking about using a tiny 2.1 megabyte patch to instantly correct facts inside a massive 16 gigabyte model. That's wild. And all of this can be run on standard consumer hardware in just a matter of minutes. All of these incredible technical solutions ultimately connect back to one fundamental philosophy: the sheer necessity of human authorship.
Section 5. The return of the author.
We really must continuously contrast the chaotic reality of the machine with the clear intent of the human. On one side, we have algorithmic distortion, the messy statistical guesswork and totally unpredictable token generation of the machine. On the other side, we have human protortion. Protortion represents the proactive execution, the painstaking effort, and the direct intent of the human architects who actively steer the machine and build its crucial guardrails.
This brings us to a deeply fascinating legal concept known as the sweat of the brow doctrine. Historically, courts granted copyright protection based simply on the sheer manual labor and effort an author poured into a work. It's like someone spending years painstakingly compiling a massive phone book by hand. Because modern AI completely lacks conscious agency or proactive intent, legal systems and computer science frameworks are quietly resurrecting this doctrine. They're increasingly demanding human labor and oversight as the ultimate proof of originality, accuracy, and control.
The documentation summarizes this with absolute perfection. Manual authorship overrides automated miasma. The only path to bit-perfect data is the sweat of the brow. And you know, that is a warning we must heed. When these continuous neural networks eventually decay, hallucinate, or suffer from semantic bleed-through, human intervention and active stewardship are absolutely necessary to clean up the mess and regain control. This process forms the ultimate semiotic bridge between human thought and digital execution. Step 1. Human intent initiates in the mind. Step 2. We painstakingly formalize that intent into rigid, understandable text or code. Step 3. A human steward must then deliberately apply and monitor that code out in reality. Code and text are not autonomous forces. They're simply the deterministic interfaces we use to safely map our imagination onto silicon. As the philosopher Hannah Arendt beautifully stated, true creation is an active, engaged doing that is completely inseparable from human consciousness. Modern AI is not an autonomous, conscious creator waiting to replace us. It is a powerful, mechanical enabler that remains completely and utterly reliant on the orchestration of brilliant human minds, like the incredible researchers we celebrated today.
Which leaves us with a final, provocative thought to chew on. As these AI systems grow exponentially more powerful and their interfaces become seamlessly invisible in our daily lives, if we stop writing the bridge, who controls the physics? Thank you so much for joining me on this explainer. Keep learning, keep questioning, and always look past the screen.